All right, so now that we've had a chance to talk about steady state, let's talk about the other case where the flux cannot be assumed to be independent of time. All right, and so I have to thank my colleague here for this, Dr. Barron. He came up with this way of kind of explaining non-steady state diffusion. And so you can imagine that you're a swimmer out in the ocean, and here's a shark over here, right? And so if you get cut, then what does kind of the diffusion situation in this case look like, right? So if you get cut initially, right, your blood is kind of located very close to you in time, right? So this is kind of meant to be position. And then if we look at over the course of time, 5 seconds later, that blood, just like the dye in the example or the coffee, right, will diffuse out into the water further and further away from you, right? And if we keep going, that keeps diffusing further and further away. And right, so this basically shows us that the concentration not only depends upon position, but also time. And so that means that the flux would change as well, right? So our concentration depends on position and time, and far enough away, at some point maybe the shark senses your blood. So that's the idea with this kind of rough example here. So let's look a little bit more then at this non-steady state diffusion. And just like we had Fick's first law for steady state, we have Fick's second law for when the concentration depends on position, x, and time, t. So our concentration is a function of x and t. That's what this is basically saying. And Fick's second law shows us this relationship, and it's what's known as a partial differential equation, PDE. And we also are assuming in this case that what we call diffusivity, which is D, so we call that diffusion coefficient. It goes by both names. That is independent of composition, and even this is not always a good assumption. But for this case, we're going to use it. So we have we have this partial differential equation that shows us that concentration is a function of both time and position. But we're not going to do much with partial differential equations or PDEs in this class. But I just wanted to show you that this is a more complex situation because we have non-steady state diffusion. What we're going to look at is a specific solution to Fick's second law. And so to do that, to solve for a partial differential equation, if you've taken that class before, that math class, calculus, one of those calculus, you may know how to solve for this. But again, not something that we're going to solve for. But just to give you an idea of what we need. To solve this, we need to know the boundary, what we call the boundary conditions, and the initial conditions. And so what I mean by that is initial conditions, what does it look like when a time is 0? And then boundary conditions are what happens on the edges, right? Or the ends of something. And so what happens when x equals 0 or x equals infinity, right? So if we're really close to the end or really far away. And so we're going to look at a situation where we solve it for what's known as a semi-infinite bar. So you can think of this as an aluminum bar, a very long aluminum bar, such that we have one end exposed to something that's diffusing in, say copper atoms. So there's a concentration of copper on the surface of this bar. And so this surface of the bar would be known as x0. And then we say it's a really long bar because we're basically saying that it goes off to infinity, right? So at some, really far off, you see no effect of the surface concentration. So that's why we assume that it's infinitely long. And so then it just gets back to the original concentration of copper in aluminum, so C naught. So those are the conditions, right? So the boundary conditions are when time is 0, the concentration the initial concentration is the same throughout the bar, right? And then after 0, we set our boundary conditions so that the surface concentration CS is that's what the surface concentration is set by the amount of copper. And then if you go infinitely far away, then the concentration goes back to C naught, which is the original pre-existing concentration of copper atoms. So those are our boundary conditions, and by applying that, we can solve the PDE in the previous expression, the Fick's second law. And so this is what that would look like. If we have position in the bar, so 0 all the way to infinity, and we look at concentration on the y-axis, we see that initially we only have 0 concentration and then the surface concentration. And then after times, you see that the concentration within the bar gets higher and higher. And so this is the type of diffusion we see. So increasing concentration further and further into the bar. And this is the solution to that PDE for this, what we call semi-infinite diffusion, is that we have the concentration at that position in time minus the initial concentration over the surface minus the initial concentration is equal to 1 minus ERF. The ERF is known as the Gaussian error function, which is here. We'll explain that more in a second. But it's equal to the ERF of the position, x, over 2 multiplied by the square root of diffusivity or diffusion coefficient multiplied by time. The values for the ERF are also in your book in table 5.1. So these are something that we're going to be able to tabulate. All right, so just a couple more notes about this expression. So when we have a specific concentration, so going back to this equation here, if we're looking at a specific concentration here, CXT, and we just call it CX here. So if this is all constant, then the other side, the right side of that equation, is also going to be a constant. And so then the inside of that, x over 2 square root of dt, is also a constant. And so we can rearrange this, and then we see that in this case, if we look at two scenarios where the concentration are the same, then the distance, the relationship between distance and time and diffusivity is also the same. And so it allows us to simplify the problem if the concentrations are the same. So that's something to keep in mind to simplify the amount of work that you have to do. You don't have to bother with the error function or anything like that. You can go straight to kind of this expression for multiple time and position, x and t. So that also allows us to come up with what we call an effective penetration depth. And so that's known as the position EFF, so for effective distance. And so that's where we say the concentration is halfway between the baseline, so the initial, and the surface, right? So at this point, the concentration is halfway in between, and so this is the depth at which that happens. And so we can basically take that expression, look at when we have half the concentration, and what that means is that that's equal to when the square root of dt, the effective depth is equal to the square root of dt. So that kind of simplifies that expression if you know everything else. All right, so in the next module, we're going to go into a little bit more depth on the error function that we talked about in this equation.